Welcome back. Statistics is an integral part of biology. Every time you do an experiment, you have to use some sort of statistics. For example, from data you calculate mean, variance, standard deviations, those are actually statistics of your data. Then suppose you are doing a population based study, for that you may have to decide the sample size. So, you have statistical tool to decide the sample size. Or suppose you have created a large data set from a population, and then you want to segregate the outlier and remove them from your analysis. Again, you have statistical tools for that. And one of the commonest statistics that most of the experimental biologists use somehow is test of hypothesis, test of significance. So, statistics is something which is integral in biology, and I will always advise every student of biology to learn statistics. This course is not a biostatistics or statistics course. There are courses available on statistics and biostatistics. I will advise you to join those courses and go through that. But even though this course is not a statistics course, there are certain statistical tools that we have to use for data analysis in the subsequent days. So, in this lecture what I will do, I will discuss about one of the very crucial thing in statistics in biology that we use is the concept of statistical test, hypothesis testing. So, I will focus more on not on all possible statistical tests of hypotheses that are there and people use them, but rather I will take one example, t-test, and through that example I will try to convey the basic key concepts of test of hypothesis. So, just like any other lecture, let us start with a data set. So, suppose we are assaying a set of molecules which are supposed to be having anti-diabetic effect. So, we have a diabetic rat model and we have taken one molecule and we have treated those as a group of diabetic rat with that, and we have a control one which is untreated. So, the data is shown here, right. I have measured the blood glucose level and I have made a bar plot. Conventionally that type of data you will see in papers and presentation. We have untreated and treated group. Now, I have also reported the mean, remember this is called sample mean, that is why x u bar we have. Sample mean for blood glucose level for untreated is 326.2, whereas for treated group it is 287. So, how much will be the difference? Difference will be around 39.2 possibly, you can do the calculation. So, I have seen the difference, right. There is a difference in the treated and untreated group. The treated group has slightly lesser blood glucose level. Now, if I show you this data, obviously you can ask me a question, is it a fluke, experimental error, or it is real? Okay, I can go back to my lab and can repeat the experiment again 2-3 times and again come with a similar data set to you with bar plot, and I can try to convince you. But remember, that does not solve the problem, because this question that you are asking me whether this result is real or it is just a fluke is connected to something more basic. Remember the idea of population and sample? This experiment has not done on population of rat, right. This experiment has been done on a sample of n equal to 5. So, I have taken 5 rat, those rat are diabetic, right, and we have not done anything to them, we call them untreated group. Whereas, I have taken another set of diabetic rat, 5 in numbers, and we have treated them with drug, we call them treated group. In both the cases, these groups are, these 5 rat in each group are nothing but samples, right. But what we are trying to know, what you are asking me after looking at data, you are asking that whether at the population level, this difference between treated and untreated group will hold or not. So, you are asking me at the population level, will we see any difference? Now, remember, I do not know what is the population, right. Population must be very large. We cannot do the experiment with the whole population. We do not know the mean, variance, all these things of the population either. As we do not know those statistics of the population, those parameters of the population, we are doing experiment on samples, and from the sample I want to project to population. So, the key question that people will ask when they will see this data is that, are the treated and untreated populations are different, not the samples. So, how should we answer it? As I said, I cannot do the experiment on the whole population, I do not know even the size of the whole population, right. So, statisticians try to answer this question using a probabilistic method, And the tricky part is they do not answer this question directly, rather they pose a bit twisted question, and that is where the tricky thing is. So, follow me carefully how I pose the question, how I will change this question. Assume that at population level, the blood glucose level for these untreated and treated groups at population level, their population distributions are same, identical, they are not different. Now, you make fresh sampling, one fresh sampling from the untreated group and another sampling from the treated group. Now, you calculate the mean blood glucose level for these two samples, untreated and treated, and find the difference in the mean between this untreated sample and treated sample. So, you will have again a new difference value will come, right. Now, the question is, what is the probability that this new difference coming from the new samples that you have taken will be greater equal to the difference that I have seen already in this experiment. The difference I have seen in this experiment is something 39.2. What is the probability that the new difference that is coming from new samples that I have sampled again will be greater equal to that 39.2? We want to calculate that probability. If that probability is very high, then my assumptions that at population level the distribution of blood glucose in both treated and untreated group are same will hold. If that probability becomes very small, then I will reject that hypothesis, that assumption. It is a bit tricky, right? We have inverted the problem almost, right? So, just try to follow it once again. What I am saying, if two population distributions are same, this is my assumption, then what is the probability? You have to calculate the probability that the difference between the sample means, you have taken new sample and you have calculated the difference in their means, the difference between the sample means be greater equal to observed differences of sample means. That you want to calculate, and based on that probability either you will consider this assumption that two population distributions are same, or you will reject that assumption. So, let me put it symbolically, that will be easier to understand. So, what I am doing here, I have two hypotheses. One is called null hypothesis, the other one is called alternative or experimental hypothesis. Let us first take the alternate or experimental hypothesis, because that is in line of the experiment that we have done and the data we have seen. In this case, we consider that the two population distribution, remember distribution of blood glucose level at the population level, not sample. The two population distribution are different. That is what we believe, that is what I want to prove, right, possibly. So, in that case, mu of u, that is the population mean, mu is population mean, right, mu of u is not equal to mu of t. Now, what is the null hypothesis of this? The null hypothesis is that two population distributions are same, that means mu of u is equal to mu of t. Just notice this one, the null hypothesis and the alternate hypothesis are actually binary and they are mutually exclusive, right. And null hypothesis does not mean that it has to have some value 0 or something like that. It is essentially negation of the other one, this alternate hypothesis or the experimental hypothesis or the belief that you possibly started the experiment with, right. So, once I have these two hypotheses, then I want you to calculate a probability. What probability? I want to calculate the probability that the difference in sample means you are again doing sampling from the population, will be greater equal to the observed difference. What is the observed difference in this case? That is 39.2 possibly, right, if I am not doing a wrong calculation, 39.2. Given, this is important, given H0 is true, that means null hypothesis or H0 is true. I have to calculate this probability and we will call this p value, this probability p value. Now, when we are talking about calculating a probability, we have to require some sort of probability distribution, right. And here we are calculating the probability of difference in sample means. So, the variable is a continuous variable. So, we need some sort of probability density function. Suppose I know that For the time being, we assume we know that. So, this is the PDF given to me, I know that, and this blue shaped, this is the PDF function, and I have in the horizontal array difference in sample means. And now, I have to calculate this probability. How should I calculate? Okay. Suppose this value is 39.2, then someone here suppose that value comes 39, I am just 0.2, right. So, then the probability that this probability P will be, actually I can draw a line, this area under the curve, this is greater or equal to the observed difference, this is the observed difference, and greater or equal to mean this side. So, this is the area under the curve, that is the probability I am asking you to calculate, and that will be the p value. And based on that probability, we have to make a decision about the null hypothesis that we have made. Now, it turns out that the probability density function or probability distribution that we have to use for this particular problem of blood glucose level that I started with, and the test that I will do will be called a t-test, we have to use t-distribution. We have studied about normal distribution in continuous random variable case. So, just let me introduce you briefly what is t-distribution. T-distribution is almost similar to normal distribution. What I have plotted here in this graph, I have plotted standard normal versus t-distribution. So, standard normal is this blue one. So, standard normal, if you remember, the mean will be 0 and the variance will be 1. So, this is where the mean is. So, the peak is at, for the blue curve is at 0, and the yellow curve is for t distribution with a degree of freedom. df is degree of freedom. I will not go into details of how degree of freedom we calculate and all these things. For the time being, we have to remember that degree of freedom is a parameter in the PDF of t distribution, and it is related to the sample size, right. If sample size is large, degree of freedom will be also large. So, what if you see this diagram, you can see actually the t distribution is also symmetric around this mean 0, and it is falling just like exponential, though it is not a complete exponential fall. The only difference is that this is a bit fatter on the tail sides, right. That is the only difference. Now, the most interesting feature of t distribution is that if I keep on increasing the degree of freedom, the parameter for t distribution, it will move towards standard normal distribution. So, let me show you this in the graph. So, I am increasing degree of freedom from 1 to 30, and the pink line is for degree of freedom 30, and you can see it is almost converging with the blue line, that is the standard normal. So, in a way I can say, as the degree of freedom for a t distribution becomes very, very large, t distribution becomes close to a standard normal distribution. Fine, we have learned t distribution, that is good enough for this lecture and subsequent data analysis also. So, let me go back to the original blood glucose problem. So, what I have done till now, I have made a null hypothesis where I have considered both the population distribution are same. So, their population means are identical, and my alternate hypothesis is they are not identical, and remember we are not going to do anything on the alternate one, we want to play with the null hypothesis. Now, to move further, we have to make something called test statistic, or a new variable we will introduce and calculate the value of that, and in this case this is called the t value. That is why I have written as small t. Fine. So, what is that t value? T value is the difference between sample statistics and population parameter. What is sample statistics in this case? Sample statistics is the mean of my sample, untreated sample, minus mean of my treated sample. So, that is I am calling sample statistics. What is my population parameter? My population parameter is mu u minus mu t. So, please notice this one, that they are actually similar thing, right. One is for sample, the another one is for the population. Both are the the difference between means of two groups. One is at the population level, another one is the sample level, the sample that you have observed, right, you have experimented with. So, for samples we call it statistics, whereas for the population we call it parameter, because we do not know those values and we are trying to project the get the value of parameter, we are trying to make a guess about the parameter, unknown parameter from the sample statistics. So, this is what I know, but usually you will not know this unless until you make some hypothesis, right. So, I have sample statistics minus population parameter in numerator, and in denominator we have standard error of sample statistics. I will come to that later. Now, what interesting thing is that I will not go into the details of the mathematics. If we assume that at population level this blood glucose thing, this that measuring variable, the variable that we are measuring, at population level it follows normal distribution. If that assumption is correct, then it can be shown that this t value, this test statistic t, the way I have defined, will follow t distribution. So, that makes our life easier, because we know the t distribution, we can do calculations on that. So, with this let me move further and calculate the t for this particular problem. Okay. So, sample statistics, what it will be? It will be x u bar minus x t bar, that is given here. Okay. Population parameter will come here. Now, what is my null hypothesis? My null hypothesis is mu u is equal to mu t. Population distribution is same for untreated and treated groups. So, their means are identical. That means, this population parameter difference in mean at population level must be equal to 0. So, I am left with only two terms, x u bar minus x t bar divided by standard error of sample statistics, means standard error of this one, this difference. The derivation of this standard error is a bit lengthy, I will skip those, and you do not also need to go in detail of that, but you should know that we can do that, because anyway in a statistical tool or function in R or somewhere we will do the same thing, we do not need to go and manually do that. So, eventually I get this formula, t equal to, I have the difference in mean from the sample, and this one is the standard error of that difference, and I have a s squared term which is given here, and remember this will follow t distribution, right. So, t distribution has a parameter, it depends on a parameter that is called degree of freedom. So, it can be shown for this case the degree of freedom will be sample size for the untreated plus sample size of the treated minus 2. So, let us plug the numerical values, because we have the numerical value from the experiment, and we get two things, degree of freedom will be 8, 5 plus 5 minus 2, 10 minus 2, 8, and the t value comes 4.7178. So far so good. We had a null hypothesis. From based on that null hypothesis, using the data of the experiment, I have calculated a t value. I know the degree of freedom. Now, I have to calculate the probability, right. So, we have to go back to the question. So, this is the t distribution. I have just drawn it for analysis. I have not to draw this one, just to explain I have drawn this. This is a t distribution for degree of freedom 8 around 0 you have, right, symmetrically on both sides. Now, if I have to calculate probability that a value of t using the definition of t that we have seen in the last few slides before will be greater equal to 4.718, that is what I have to calculate, right. If I freshly sample from the same population, then again I calculate, do experiment, and again get the values and calculate t. So, that is my new t. I have to calculate the probability of getting that t greater equal to what I have done already. I have got this one already. So, I want to calculate this probability. So, how should I do that? Let us look into the diagram. So, this is 4, our t value is 4.718. So, it will be somewhere here. I cannot draw it, but somewhere this area will be area under the curve, and you can easily see that area under the curve will be very small. That means, the probability, this probability that t will be greater equal to 4.718 will be very small, and I will show you the value. So, it is a very small probability, but there is an issue here. See how I am calculating the difference in mean? I am taking xu bar minus xt bar. Why can't I do the reverse thing? Take the xt bar first and subtract xu bar then my all values of deviation difference in means will come in negative for this data set and my t value will come minus 4.7178, right. So, let us check what will be that probability. So, here this one will be again very small, but as the difference can be both negative and positive, I have to consider both the probability and they will be identical. I will simply add them, I will multiply by 2. So, that is what I have done here. The probability that t is greater than the absolute value, so that I am not bothered about the sign, absolute value of 4.7178 which I have got for my t value in my experimental data, right. It will be greater equal to anyway actually. So, that will be, and then I multiply with 2 because I have p both side. So, that will be 0.0015. One thing just to mention here, as I have taken the calculated the probability from both side, this is called two-tailed. If I have reasons to believe that one side is good enough, that make a physical meaning, that is a meaning, biological or physical meaning for that, then that will be one-tailed, right. So, this is a two-tailed probability I have calculated and that has come to 0.0015, good enough. I started with my data, I made null hypothesis, I made alternate hypothesis and I have got t value, degree of freedom and I have got the p value also. Now, remember my initial question. My assumption, my null hypothesis is that at population distribution of blood glucose for these two groups, treated untreated are identical, their mu's are same. And then I calculated the probability of getting this situation and that probability has come to 0.0015. And as I said at the very beginning, if this probability is very low, I will consider that null hypothesis is wrong, my assumption is wrong. If this probability is very high, then I will be sure that this hypothesis is correct. Now, larger, bigger, smaller, these are a relative term. There is no absolute small or something like that, right. So, when I say probability is small, what do I mean? How small is small? So, that is why I have to use a cutoff, I have no other option. And in this case, this cutoff is called level of significance and usually represented by a symbol alpha. Suppose we have agreed, you and me has agreed that level of significance, that cutoff will be 0.05. Now, how do we agree? It depends upon the convention among the people, scientists who are working in a particular field. It also depends upon how sensitive the assays or experiments that you are doing. If you have a very sensitive assay where you can make measurements suppose up to 10th decimal point, obviously you will go for a very lower cutoff value, right. So, how reproducible the results are, all these issues are there. Based on that, we have some thumb rule. In every field there is a thumb rule and many a time in many biological thing it is 0.05, some experiment you may consider it is 0.001 also. So, this is a cutoff. So, this is called level of significance and in my case, in this particular problem, what has happened, this p value is lesser than, because this is lesser than my cutoff. So, that means the p value, the probability that the t-statistic that I have calculated for a new sample from the same population will be greater equal to the existing t-statistics that I have seen in my experimental data, right. That probability is smaller than the cutoff. That means my null hypothesis has to be rejected. So, I reject null hypothesis. If I reject null hypothesis, what do I left with? Because my hypothesis is a binary, I have two binary hypotheses. If one is true, other one is false. If one is false, the other one is true. So, if H naught is false, then my alternate hypothesis is true. That means the mu the population mean of untreated and treated group are different. That means, in other words, the treated and untreated population, not sample only, sample you have seen the data, at population level the treated and untreated groups are different. So, that is my conclusion. So, till now I had not dealt with the alternative or experimental hypothesis, I was still dealing with the null hypothesis. Once I rejected the null hypothesis, I reached to the conclusion I want to draw at the very beginning. So, this is how you do t-test, and hopefully I could communicate the basic essence of hypothesis testing using that. Let me generalize what you do in a test of hypothesis, any sort of test of hypothesis. You first make two alternate binary hypotheses, null hypothesis and alternate hypothesis. Null hypothesis does not mean that something has to be 0. Null is negation of the other one. Then you define some sort of test statistics. In this our case we have done the t, right, t value. It may not be t for something, some other tests. Then what you do, you calculate the probability that the test statistics is greater or equal to the observed test statistics given the null hypothesis is true, and that you call p value. Now, you compare that p value, p value with some significance level alpha, and based on that comparison either you reject or accept the null hypothesis. This is what is test of hypothesis, or some people will call test of significance. These are called parametric tests because in all these three cases I have given the example here, you have to make some assumption about the population distribution, right, and that assumption is actually the population distribution is normal. That is what I mentioned also earlier. For t-test, initially I assumed that the population distribution of blood glucose in both the treated and untreated group are normally distributed. Whereas, there are certain other hypothesis tests like the Mann-Whitney test, right, where you do not make any explicit assumption about the population distribution behind your sample, right. So, those are called non-parametric, and they are many times very useful when actually your population that you are dealing, the case you are dealing with where the population may not be normally distributed, right. Now, we have almost reached the end of this lecture, but before I move to the key points, I want to highlight certain important issue which many a time we miss while using statistical test of hypothesis or test of significance. The most crucial thing is that statistical significant is not equal to significant. What do I mean by that? See, something which has come out to be statistically significant, that does not mean that that observed behavior or observed change that you have seen is important, relevant, or very big or very small with respect to the biology or clinical implications, right. For example, in our experimental data that we discussed, we have seen the difference between treated and untreated groups blood glucose level is statistically significant, but that does not tell me whether that difference is biologically significant or not, biologically relevant or not, whether that will affect the longevity of the rats or not, whether that will affect the metabolism of the rat or not. We do not know all information, all this information are absent to us, right. So, we cannot conclude about the biological or clinical implications from a test of statistical set of significance. That we have to remember. That is why it is said, whenever you are writing in a report or you are giving a presentation, you are writing a paper, do not say the observation is significant. If you have done a statistical test, for example, t-test or ANOVA, and you are talking about statistical significant, then you write the observation or the difference is statistically significant. That is all, that phrase you use. And if you want to mean that some observation is huge, or some observation has a huge implication in a case of biology or clinicians, right. So, in that case you use those type of terms, like these are important, this is relevant, this is a big, something like that, but do not use the word significant, because then people get confused. The other thing that we have to remember is the statistical significance is all about rejecting or accepting the null hypothesis, right. This is corrected to this other first one, but we have to repeatedly remind ourselves what we are dealing here is nothing but whether we can reject or accept the null hypothesis, right. And the last one is that many a time we forget that statistical test of significance, the result depend upon the sample size. So, if your sample size is large and in another case your sample size is small, the same experiment, one will be statistically insignificant, the result of other will be statistically significant. So, there are lots of ifs and buts in use of test of statistical significance or test of hypothesis. Many a time we forget those ifs and buts, those issues, and that is why many a time we use wrong test of hypothesis, we misinterpret the result of test of hypothesis, and we should avoid them. And in fact, there are alternatives to statistical test of hypothesis also. For example, there are certain Bayesian method based on Bayesian Bayes theorem to give answer similar questions. So, some people insist that we should not use this test of hypothesis, rather we should use those Bayesian method. But for the time being, test of hypothesis, as we have discussed here, is going to stay in biology, and we should know how to use it, we should know how to use it judiciously. So, let me jot down what we have learned. The first thing we have learned, the purpose of hypothesis testing. The purpose is to know, does the observation made in the sample hold true for the population or not, right. That is the main question that we are trying to answer. To answer this question, what we do, we create a null hypothesis, then we make a alternate hypothesis, these are binary mutually exclusive, and then we do some create some test statistics depending upon the what type of experimental data we have, and then we calculate a probability that the test statistics is bigger than observed test statistics, considering the null hypothesis is true, and we get the p value, and we compare that p value with a cutoff called significance level alpha, and based on that either we accept H naught null hypothesis or reject that. That is how you do all sort of test of hypothesis, and we have discussed only t test in this lecture. We have shown t test to compare means of two groups, right. T test we will use in our subsequent lecture to find the significance of, or rather the statistical significance, if I say correctly, of parameters in a model. So, you have data, from that you create a model, right. So, you have some constant term called parameter in that model, and you want to know whether those estimated parameter values are significant or not, statistically significant or not, and we will use t test in that case. In some case we will use ANOVA. So, anyway we will be using test of hypothesis. And the last one that we have to remind ourselves continuously is that statistically significant does not mean that the observed changes or differences have biological or clinical implication. So, I will end this lecture with this important point to keep in your mind. It is easy to use t-test, ANOVA, because almost all the statistical software has those, just a click away. But we have to keep in mind the implications we have to of this statistical test, and we have to understand the result very judiciously. So, I will, just like other lecture, I will leave you with a problem to solve. I have experimental data here. So, what we are doing, we are trying to suppose generate some inhibitor for an enzyme, and we have done an assay. We have a control, that is untreated enzyme, the other one is with the inhibitor, and the data is shown here, right. The number of samples here for control is 5, and this one is also number of samples 5. So, degree of freedom will be sample plus sample number minus 2, and I have already given you the t value. I have calculated this, that is 3.855. So, what you have to do at home? You have to check out, is the difference between these two groups, this one and this one, is statistically significant at the level of 0.01. That you have to test. And to do this test, you have to use some sort of t distribution. Earlier days people used to use t tables, but nowadays in a computer you can get the whole t distribution, you can calculate the exact value, p value. So, t tables are becoming redundant, that is why I am not insisting you to use t table, but rather you require some tool to calculate the t distribution, to calculate the probability, right. So, there are online tools also. One example I have given here, but if you do a search on the web, you can find something else. So, use that tool and find out the answer to this question. Is the difference between these two groups statistically significant at the level of 0.01? That is all for this lecture. See you in the next session. Till then, happy learning.